Today we have a fascinating conversation with Professor Pedro Domingos. Remember, if you like content like this, consider hitting the subscribe button and rate us on Apple Podcasts. And by the way, our friend Pedro has written this book called The Master Algorithm. I highly recommend you buy yourself a copy. It's absolutely fascinating. Actually, I think we're going to consider making some content on this book. So if that's something that interests you, let us know. Anyway, enjoy the show.
How are you, sir?
Yo.
Good. How are you?
We are very good. We're
Good to see you again.
Yeah, good to see you. How's life?
Yeah. Life is good as much as possible in these troubled times.
Yes, I know exactly what you mean. Right. So I'll tell you what, could you just give us a quick piece on your book, The Master Algorithm?
The Master Algorithm it's an introduction to machine learning for a broad audience. I decided to write it because I realized that we were at the point where everybody needs to know machine learning, not just the specialists. You know, as a private citizen, as a decision maker, you need to know not the mechanical depths of how things work, but have a conceptual model of what a machine learning system is doing. And so I wrote a book covering the main styles of machine learning and also what its main consequences in the world today were at the time and in the future being now. And a lot of that I talked about in the book is in progress, even in ways beyond what I imagined. So, yeah.
I'm curious about that. So, and not that I disagree at all. Why do you think it's important for kind of like the general population really to understand machine learning, and like what do they need to understand about it?
Exactly. As I said, they don't need to understand, LBFTS and stochastic gradient descent. They, here's an analogy that I've often used. You don't need to know how the engine of a car works. That's for the mechanics and the mechanical engineers. But you do need to know how the steering wheel and the pedals work. Otherwise, you're not going anywhere. And in a way, machine learning today is like a car that arrives at your door and says, "I'll take you where you want."
Could I push back on that a little bit? We spoke to Melanie Mitchell, and she was talking about the four fallacies in AI, and things like there was the first step fallacy, so assuming that we're on a continuum to artificial general intelligence, and the lure of wistful mnemonics was another one, I think, and also that AI should actually be embodied. And just to push back on what you said a little bit, even actually some people think that statistics and artificial general intelligence are somewhat synonymous, right? So you kind of do need to know a little bit what's going on, right?
No, look, okay, so let's dig down to a slightly finer level, right? You need to understand it at different levels for different things, right? But there's even let's just start at the most basic level, right? Is that I saw a lot of people, and I still see, including CEOs, making decisions about machine learning that are very costly because they haven't a clue what machine learning is. And related to that example, there's a whole galaxy of misconceptions about machine learning and AI more broadly, with which it's conflated these days, of course, improperly, which is confusing artificial intelligence with human intelligence. And I hope that, people who read the book will gain a few things. One of them is that they will never have that illusion again that AI is like human intelligence. It may be, right? Again, I cover that. Many strands in AI are come out of psychology, and I think that's good. But fundamentally, to give you the technical definition, right, AI is solving NP-complete problems using heuristics, which is a very different notion from what you see in the press and the people talking about, Terminator and AI bias and whatnot, right? There's this expression that I really like, which is the homunculus fallacy. I don't know if you heard this. The homunculus fallacy is the fallacy that inside every AI system, there's a little man pulling the strings. It ain't like that. And then for us, it's funny. But for a lot of people, it's that's the mental model that they have because they've never been given a better one, right? So, to answer your question more directly, as an individual, right, you need to realize that you're interacting with computer systems all the time that are making decisions on your behalf that are guided by machine learning. And at that level, you don't, you can even just have, imagine that all it's doing is logistic regression or naive Bayes, right? At that level, it's enough. There's these attributes, it's making predictions about you based on correlations between these attributes. This captures epsilon of machine learning, but is already, important for people to know. But then as a professional, for example, I think one of the most important things that like your use of machine learning as a professional can go all the way from being, a hotshot machine learning PhD who knows all kinds of math and logic and statistics and optimization and whatnot, to someone who uses AI tools without knowing the AI inside them. Of course, that's not ideal, but in between these two extremes of the spectrum, there's many different levels of understanding. For example, you should be able to build models. This is something that I've worked on a lot because I think it's really important. It's like, you should be able to build, this is what Markov logic is for. You should be able to build models of your domain, whatever it is, combining data with all your expertise, without having to understand the gory details of how machine learning works. You need a language in which you express what you know and in which you interact with the AI. So you should be able to teach that AI, right? And you're right, at this level, you start to need more than just use the steering wheel and the pedals, but you have to start at the beginning.
Maybe you could clarify a bit for me, the audience, the intended audience of the book, because I can certainly see some segment of the population, or expanding, let's say, the segment of population that can understand some of those concepts. But on the other hand, we have a long history of lots of people misunderstanding very basic concepts like correlation is not causation, for example. And especially when you get into probability theory, there are prominent examples of even mathematicians and certainly scientists and for example, medical doctors, that it's just not intuitive to get a lot of the concepts in probability theory. And so what about that? I mean, is the hope that we can somehow break through that barrier, or is it more you're targeting, let's say an engineer who needs to learn something about machine learning in order to, like you're saying, build models that can help them at work?
I'm actually targeting all of the above. And in fact, I think a lot of the art of writing a book for a general audience, and I really looked into this with examples from, positive and negative examples of this, before I wrote the book. If you can at all, you should try to write a book that works at multiple levels. Someone should be able to read the book superficially, and many people have, and get something out of it. But that was definitely not just what I was shooting for. I was actually very determined to actually have a serious coverage of essentially all of machine learning at a certain level of abstraction, of course. But like, you got to come out of that book. Again, one of my pet peeves has been that like people learn type A of machine learning. These days it's deep learning, but it could be kernel machines or, Bayesian learning or whatever, in school, and because they were taught randomly by the people who were of that persuasion. And then they think that's all there is. And then they go through their life applying their hammer to everything that now, of course, looks like a nail. And that's very costly, right? So I also want people, if I had to say, like, at the end of the day, who were the people who most enjoyed the book? They were actually people who have some technical background, but are from other fields, right? Because there's there's a lot of, real math and engineering and stuff in science in that book, kind of like stated in a way that's accessible. But if you know that, you actually, you feel it, and you like seeing the connections made. And again, I said that in the introduction to the book. Even if you're a machine learning pro, I hope that you will learn a lot of things from this book.
Yeah.
And I think a lot of people have. Now, who are the people who have most benefited from reading the book? I think it's like, it's the CEO. Like there was this book that I think George Miller wrote many years ago called Physics for Future Presidents. It's like, if you're going to be the president of the United States, you don't need a PhD in physics, but you need charge of a nuclear arsenal and blah, blah, blah. So, there's some things that maybe you ought to know. And like one of my, clusters of audiences for the book was like the CEOs. And indeed, I know countless CEOs who really liked the book, right? And have told me so, because they needed to catch up on machine learning like badly. And they're not going to read the textbook. So it was a godsend for them. Just to give you an example, Jensen Huang, right, the CEO of NVIDIA, right, this happened at the time that he was pivoting, from gaming to AI. He told everybody at the company to read the book, period. And they did.
Wow, amazing.
So I still have, NVIDIA were coming up to me saying like, oh, I read this and I like this and I have this question. So, these are all parts of the audience for the book.
Could I pick you up on a couple of things? So I'm very interested in, I said about Melanie Mitchell's lure of wishful mnemonics and anthropomorphization, because I think you resent the anthropomorphization of these machine learning algorithms. And your recent paper actually kind of showed that there was a kind of an analogy between many of these machine learning algorithms. And that's why I want to take a step back, because you could see many of the empirical and statistical approaches to AI as being somewhat analogous. And there are some very divergent conceptions of what AI is. We spoke about the embodiment, for example, but psychologists separate the mind from the brain, and there are emergentists, for example. Do you think there's any value in conceptualizing? Sorry, just to go back to the beginning. You were saying that people didn't really have any deep understanding of what's going on, but the level of abstraction is important. Your frame of reference to understand this is important, right?
Well, you said the word there that kind of pricked up my ears. It's not that there's an analogy between these different approaches. It's much deeper than that, right? The paper that you just referred to, it's actually showing that every model learned by gradient descent is a kernel machine. So maybe at the end of the day, all the machine learning that we've been doing, prominently including deep learning, is just kernel machines. So as much as I want people to learn the full spectrum, the variety of machine learning algorithms, I don't want it to be a collection of stamps. That's not good science. And in fact, the story of the book, right, is that there's the 5 tribes of machine learning, the Bayesians, the connectionists, the symbolists, etc. And then we visit them and learn their way of doing things and their wisdom. But then the goal of this whole process is to find the master algorithm, right? And there's a chapter in the book where we put these things together, and there is a master algorithm. And in fact, that chapter has held up very well. And this paper that you just talked about is another step in that direction. So I think when all is said and done, right, we do, machine learning is not a hammer, and it's better to have a Swiss Army knife, right? But a Swiss Army knife is still 5 tools jammed into one.
Right.
I think what we're going to understand is that at some deeper level, all these things are really just, variations on the same theme. Right? Think of different regimes of the same equation. But right? That's I think where we're going to
on that though. If we spoke to a symbolist, they would say, yeah, all of those machine learning algorithms are the same. And if we spoke to an emergentist, that would be a completely... we spoke to Ben Goertzel, for example. He's a great example of an emergentist, and also Jeff Hawkins as well. But no, there are some completely different frames of reference here. And you could quite easily just conflate all of the machine learning empirical approaches and just say they're all different sides of the same coin, right?
Well, so this is what I love about it, is that, so first of all, there are people who don't believe in this idea. Right. The quintessential example is Marvin Minsky, right? Marvin Minsky's whole theory of mind is that it's one damn thing after another. There is no unified theory of the mind, right? I don't know if you read The Society of Mind, but it's literally 200 chapters, each about, one of 200 different things, right? And I understand that, but, so there's people for whom, what I say the master algorithm in that chapter doesn't make sense, right? And I respect their opinion, but the fun part is that of the people who do believe in the master algorithm, and I actually think that deep down almost all machine learning people believe in it, because the point of machine learning, and this is how I start the book, right, is to have algorithms that can learn anything. That's the magic of it. It's like it's a general algorithm. It's like the master key. That's where the name comes from. That opens all locks, right? But then the thing that's kind of like hilarious almost to me is that like the hardest core believers in every one of these schools, and Rich Sutton with reinforcement learning and Jeff Hawkins with his theory, they do believe that all algorithms are the same, namely theirs.
That's right.
But part of what I explained in the book is like no, it doesn't work, right? I say that like there's these 5 major problems in machine learning, that in AI, that you have to solve. And these different algorithms are very good for solving different ones of those. For example, the symbolists are the ones who can learn composable knowledge. Backprop solves graded assignment. But what you got to realize, and I give examples this in domains like, robotics and fighting cancer and whatnot, like you have to solve all 5. So if all you have is backprop, you're deluding yourself. That backprop is going to, I have this ongoing argument with Jan LeCun, where he says that like, AI is going to be solved by gradient descent. It's all gradient descent. You either do gradient descent or gradient free optimization, and gradient free optimization is hopeless inefficient. So ergo, AI is going to be solved by gradient descent, which to me just sounds, I really respect Jan, and I agree with him on a lot of things, but on this one, I just can't fathom his blind faith in backprops. So there's a lot of this in AI, and the book is definitely confronting that head on.
Yeah, I mean, we're so interested in open-endedness, and we love Kenneth Stanley, and he gave some examples of some open-ended algorithms that beat gradient-based reinforcement learning agents. And because a lot of people say, well, evolutionary algorithms are rubbish, right? Because they're not principled. You have this random mutation and it's not principled. But demonstrably,
I mean, for evolutionary algorithms, right? I had the chapter so they're one of the tribes, right? The evolutionaries. Mm-hmm. And many people in machine learning, when they saw the book, said like, oh, why do you have the chapter about this? Nobody does it anymore. It's not machine learning. I'm like, there's a whole big conference dedicated to this, and they're growing as well. And I mean, it's not in principle, right? Again, you can debate the ins and outs of this, but I do believe there's a lot to come from looking at that. I think the problem is that we do not understand evolution well enough yet. Right? Yeah. We have a cartoon of evolution.
Exactly.
And that's why we're not doing it better. But we need to work with evolutionary biologists and the people who do evolutionary game theory and all that. And I think very important things will come out of that. Same on the optimization side. And we do not understand the brain well enough. And, when we do, we'll think that the idea that the brain learns by gradient descent is a joke. I mean, the only part of the brain that even remotely looks like it could be run by backprop is the cerebellum, right? There is a certain similarity between the cerebellum and backprop, not the cortex, as Jeff Hawkins will tell you, or probably told you in gore detail. But even there, right, the most notable thing about the cerebellum, which is for learning mainly motor skills, is that once you learn a skill, you never lose it again, right? You learn to ride a bike when you're 6 and it's with you forever, even if you don't ride a bike for 40 years. Contrast that with the catastrophic forgetting that is the signature problem of backprop. So, we're very far from understanding how these things work. So we need to understand them better. And then we need to, bring those ideas to AI as we have very successfully in the past. And also, I think those fields would benefit from the ideas that we come up with in AI, right? I like psychology, I like evolution and whatnot. But at the end of the day, it's so much more satisfying to be an AI researcher because you get to make progress so much faster with computers than with doing experiments with people or things like that.
I know there are so many fascinating things to pick up on there. Jeff Hawkins is looking into...
Hold on, before we leave that topic, I wanted to bring up something specifically about learning from the brain. I wonder if you're familiar with Blake Richards at all, mm-hmm. in his work about the neocortical sort of microcircuits and pyramidal neurons. And what was interesting about a presentation I saw him give is he was asking the question, okay, we pretty much know the brain can't implement gradient descent, biologically the way it is. But what they figured out is that it appears to implement something that's like a stochastic kind of, version of gradient descent. And I think exactly what you're pointing out here is that we can learn a lot from that, so there are some ways in which that stochastic sort of gradient descent can actually outperform gradient descent, and they're doing experiments on that. And it's worth at least exploring, right? Like what the biology is doing.
I mean, it's definitely exploring, and I sympathize. But first of all, stochastic gradient descent is what everybody uses for everything.
No, I'm not talking about it. Yeah, it's different.
Yeah, I understand. Yeah. But my feeling about the work of people like Blake Richards is that they are trying too hard to make the brain fit what we think is learning, coming from an ML point of view, right? I've seen this, happen. It's like the brain is so complex that it manages to look like anything we want it to look like. And people, Yoshua Bengio is another example, right? Like they've come up with many ways of trying to say but this is how the brain really does backprop. My feeling, and it's just a feeling, is that the brain just doesn't do backprop. It does predictive coding. Predictive coding, I think, is a very important idea. And, if I had to guess, looking forward, when we understand how the cortex learns, it will be predictive coding. Again, our understanding, predictive coding is an old idea. In fact, there's a lot of new confirmation of predictive coding coming out of the neuroscience, which I think is very exciting. Not enough to change. The other problem is that the neuroscience under-constrains the algorithms. We don't know enough to decide what your algorithm is going to be, right? So it's a very, leaky interface between the two sides. But if I had to, which doesn't mean it's not worth it, but at the end of the day, neuroscience at this point does not so much constrain you as maybe give you inspirations. And I think, to my intuition, predictive coding is actually how we really learn. And again, what we do is we do predictive coding, and then we remember. In machine learning, we have this unfortunate distinction between memory and learning. If you remember, things are overfitting. But again, if you go back to this notion of that we talked about gradient descent learning kernel machines, right? What it's really doing is remembering the examples, except very efficiently in a superposed way, right? I think this combination of predictive coding and superposition, my guess is this is not the whole story, but this is really a core part of how the brain learns. Now, you can take any function, right? And that I'm optimizing, right? And as long as it's continuous, and say that, this is, take whatever differential equation your system obeys, and you say this is gradient descent on something, right? You can always, if you have a function, you can always think about its integral, its derivative, right? The question is that helpful? Sometimes it's helpful, sometimes it's not. And again, my feeling, I can't prove this, but there's a lot of work that I think is pointing in this direction, is that don't think about gradient descent. That's actually the wrong way to think about it. Think about the differential equation that your system is following, right? It's descending the gradient of the loss, right? But it's a differential equation, right? And the fact that was the gradient of something is actually secondary. Another question that we should be asking is why is this the differential equation that, an intelligent brain uses? I think the real differential equation is going to be, even staying in, continuous land, which you can, right, is going to be something much more interesting. And I don't think it's going to be anything humongously complex. It's going to be more complex than gradient descent, but it's going to have a much more interesting and more powerful dynamics. The thing about it is that, as a dynamics for learning, gradient descent is kind of very limited. In fact, I said this thing to Jan on Twitter, not to Jan. I said this thing on Twitter that Jan then replied to a little defensively, and it was just this. People who believe that intelligence will be solved, by gradient descent need to explain how scientists do scientific discovery using nothing but gradient descent. Right? And I think this sentence alone makes it obvious that it's not all just gradient descent, right? They're not even using gradient descent, let alone it's all gradient descent, right?
Could I ask you a little bit about that? So we're speaking with Numenta, by the way, and they've really leaned into sparsity, and we've spoken to Jonathan Frankel, the lottery ticket hypothesis. And, for neural networks to use gradient descent has to work, right? So it turns out gradient descent works much better on dense MLPs. And actually, most of the architectural tweaks in neural networks are to make the optimization more amenable to gradient descent. But sparsity is interesting, isn't it? Because the representation is much more robust when you sparsify the network, because you kind of tell it to forget about all of the low frequency instances. So are we in a bit of a catch-22 where we can't train the things, into a sparse network directly?
Well, so, I agree with you. So gradient descent works, right? And I have nothing against gradient descent. I use it myself all the time, right? And I've even written papers too on proving gradient descent for certain, representations, like subprod networks that we've developed and whatnot. But you're right. The thing is that a lot of the work people do today is shoehorning everything to make life possible for gradient descent. And this, at the end of the day, is actually very harmful, right? I think when people look back 20 years from now, if they even bother to, they're going to be horrified at these Byzantine concoctions of learning these, bazillions of parameters, 99.9% of which were redundant, right? But why do we need them? Because we need them to make life easy for gradient descent.
Right.
Now, sparsity is a very important idea for many reasons. One of them is that energy consumption is the number one constraint on what the brain does. Your brain, even at rest, consumes a quarter of your energy, right? This is mind-boggling, right? In fact, apparently, cows have much more powerful digestive systems than humans have, but we have to give up on that in order to free up energy for the brain. So, we have a different ecological niche, right? But the point is that energy consumption is really, really a strong constraint. And we forgot that during the first 50 years of AI. Now it's coming back for different reasons because of data centers and mobile and whatnot. But sparsity, if you talk, when I talk to Jeff Dean, one of the things that he's always saying is that we need sparser networks. I'm like, what is your wish list? And number one is, we don't want this whole network to be on at the same time, right? We want just a small amount, and which is what happens with your brain, right? Most of your brain isn't on most of the time. And same with the connections, right? So I think there's a lot to be done there. Now, to me, the most ironic part of all of this is that people now forget that, deep learning, the modern age of deep learning, starting circa 2002, 3, had 3 phases. The first phase was the pre-training, right? I remember when Jeff Hinton was, this was the thing, right? And that, that did some things like, it was good for speech and whatnot. But then there was a phase that no lies forgotten that was all about sparsity. It was sparse coding all the way. I remember talking with Andrew Ng, at, like maybe the second deep learning workshop when there were only 50 of us. It's kind of, hard to remember that now, but we all fit in a room with the posters around it. And Andrew was very gung-ho, right? And he said, like at the panel at the end, something like, I don't want to put words in his mouth, but like, we're going to solve AI now in no time, right? I'm exaggerating a little bit, but that was the spirit of what he was saying. And then at the end of it, I asked him, right after, I was like, so, wow, tell me, how are we about to solve AI? And you know what his answer was? I think he would be embarrassed to hear this now, but like his answer was, well, we now know how V1 works. V1 is sparse coding. And all the brain uses the same algorithm, therefore we know how the brain works.
That's kind of like the 1,000 brains perspective.
I mean, he was influenced by Jeff Hawkins. I don't know if you know this.
I quoted him in the show. He said that Jeff convinced him in his first book on intelligence that human level general intelligence could be explained by a single learning algorithm.
Indeed, right? And in fact, the master algorithm's first working title was the one algorithm, right? So we're really all in the same wavelength here. But my point was that there was a point at which sparsity was the deep learning thing. And then of course, AlexNet happened, and we're in the age of AlexNet still, right? Where on the contrary, we learned these massively dense, redundant, over-parameterized things because we got GPUs to learn them, right? I mean, GPUs in a way are like this joker in the deck of AI that scrambled everything, right? I mean, GPUs just gave an unfair advantage to a particular set of techniques.
Right.
Yeah.
The machine lottery.
But just to close the loop on that, these models are not trainable without starting from a dense model, as far as I'm aware. Even the sparsification algorithms, usually they start with a dense model and then they prune and prune and prune. SGD just doesn't seem to work without a dense model.
No. Well, so there's a couple of different things here. You have to distinguish sparsity at learning time with sparsity at performance time. Google, for example, really cares about sparsity at performance time because they pay the electricity bill. Seriously, right? If you decrease their, I mean, like, if I had to guess, like, and it's not completely a guess, the great majority of Google's entire electricity bill these days consists of running deep learning algorithms at performance time, right? Their electricity bill is all those redundant connections, right? So yes, you can. It's the same thing with systems on the edge, right? Which are very popular. Google has the latest Android phones have TPUs in them. This is how far we've gotten, right? And and a colleague of mine just sold his company to Apple, and what it does is it sparsifies networks down to 1 bit per weight, and then they work a little bit worse, but still well enough, right? So this kind of performance time sparsity is very important, right? Now you're talking about learning time sparsity, right? Learning time sparsity is not as important, and the thing there is that if you follow there's learning inspired by the brain, and there's the connections paradigm, which is actually a very impoverished version of learning by the connections paradigm is like your structured learning is learned. There is no structured learning. Therefore, you have to start out with a redundant structure because that's all you can do. And now if you ask the symbolists, they'll pull their head out at this because we can do discrete search. We don't need to do that, right? We can do architecture search. And again, I do that all the time as well. And it's ridiculous not to, but it's there's this, I don't want to say ideological, but there's what I've noticed is that the deep learning people don't like the idea of learning structure. It's it doesn't agree with them because they have this the brain, and then you talk to evolutionists and they're like, you're just tuning parameters. The real learning is discovering the structure of the brain. So structured learning, in my view, is an essential part of the master algorithm. And then, you can be as sparse as you want at learning time. In fact, when you learn a Bayesian network, or a set of rules, typically you start out from zero, the null model, right? So why not do that? There's nothing wrong with doing that.
Well, because you can't, if you don't invent the structure yourself, you can't give it a cool name like horseshoe or, something like that. It has nice symmetric shape. But I want to come back to your predictive coding point, which is that Joshua Bengio has frequently been talking about the importance of simulating like the world models. And for example, we've been looking at his GFlowNet paper lately, which also hits upon the energy thing. How can I simulate possible worlds efficiently and with some tricks, to make it better than just say MC. I'm wondering if you can talk some about the connection between predictive coding and really the simulation of world models as a core component of learning, really, at least the way humans do it, and also any comments you have on Bengio's recent work.
So I definitely believe at a certain level, at least in this idea of simulating the world, and it's inextricably tied with predictive coding, right? Predictive coding is you have a model of the world, you predict using it, and then it's the errors that are the signal that gets propagated. Among other things, this is very efficient energetically because it means, and again, there are decades of psychology showing that like what your brain is doing actually starts at the retina. Is like you're just throwing out all the information that you can throw out, right? And you can throw it out because you have a model of the world. In fact, the whole point of memory and intelligence in ways is to have that model of the world, right? And if you talk to Gary Marcus, he's always pounding on model of the world. If you talk to Jan LeCun, he's always talking about model of the world, right? And to take maybe an even better example, if you look at what Josh Tenenbaum's group has been doing, right, for a long time, is this whole idea that like, I generate the model of the world and then, and that's what I use for everything. And then, comparing it with predictions so at some level, I completely agree with this idea. Okay. But now I think, in many ways, the ways that different people have been pursuing this, including Joshua and Josh and whatnot, I'm a little queasy about them because again, come back to the human brain, right? And having a big complicated model of the world is a very costly thing, right? So this idea that what you have is a generative model of the world, right? Once upon a time, I believed in generative. There's a lot of people who say, and I think Josh is one of those, and Jeff Hinton too, in a strange way, right? They all believe in generative models, right? Maybe what Jeff Hinton and Josh originally call a generative model isn't what you really call it. There's some overloading of vocabulary going on here, but what is a generative model? At least in a formal sense, it's a probability distribution of how the world generates data. Right? If you're a Bayesian, right, and Josh is a Bayesian, right? These days he plays a deep learning person on TV, but deep down he's very much a Bayesian, right? Is you have a probability distribution from which you generate, can generate samples, then you can also update that with the data, and and then you get your posterior and whatnot, right? And the problem, this is a very attractive idea, right? And I've had arguments with prominent people in machine learning, less so these days because of deep learning, where they say like, you either doing generative learning, what you're doing is unprincipled. Discriminative learning is unprincipled. Discriminative learning is a hack. Generative learning is what's real, right? And I understand, when people are influenced by physics and whatnot, that's how they will think, but this is wrong.
Well, could I come in on that? Because this is very analogous to, we were saying before with evolutionary algorithms. Oh, it's unprincipled. So with Josh Tannenbaum, let's say dream coder, because I know he's done some Bayesian stuff as well, but that's very much a neural guided discrete program search. And you could argue that, it's a factorial search space, but apparently this neural network makes it a linear search space, but seems a little bit dodgy, doesn't it? But what Hinton's doing is he's got this neural network that models instinct. So with AlphaGo, we actually did this this Monte Carlo tree search, and that really is system 2, right? I mean, first of all, it's a bit weird that we're modeling it as discrete actions. You're talking about the brain a minute ago, and it seems a bit muddled in my mind to talk about predictive coding and then talk about traversing, discrete actions. But let's stick with the actions. Now, Hinton doesn't say that this is reasoning or system 2. He thinks that instinct is something completely different, but it still should be modeled with a neural network.
No, but okay, we're bringing in a different set of issues here. I don't know if you've heard, Danny Kahneman's diatribe against people like Bengio talking about system 1 and system 2.
Tell me, I'd love to know.
Yeah, he's like, what these people are calling, he says they, again, not to put words in his mouth, but he says they're completely confused, right? What a lot of these deep learning people have been calling system 1, system 2 isn't, right? So the cartoon, and this is a powerful cartoon in our community, is that, and I mean, you've heard this many times, is that system 1 is perception and system 2 is reasoning. And deep networks are good at, and we've mastered system 1. We got deep learning. System 1, we got that down, right? But now, right, to achieve full intelligence, we need models of the world and reasoning and all of that. And that's system 2. So now we got to do that as well. And then Kahneman looked at this and says like, no, that's not what I meant. The model of the world is system 1. You guys haven't even remotely figured system 1 to begin with. System 1 is everything you do automatically. Again, I'm oversimplifying, but this is a better approximation. Like system 1 is everything you do automatically. Think of everything you do automatically. In fact, it's because you have a model of the world encoded in your neurons that you can do so many powerful things automatically. And then when that doesn't, and system 1 is what we do every moment, of the day. When that doesn't work, then you get into this slower, harder search process that we call conscious reasoning. And that's what system 2 is. So we haven't figured out system 1 yet. I wish we had, but that's actually the bigger challenge, right? Is that in many ways you could say that the criticism of symbolic AI is that you're trying to build a system 2 without a system 1 under it. And that's not going to work. And now to get to this question of AlphaGo and instinct, what AlphaGo does, I think, is extremely interesting in a way that most people haven't noticed, and that I think is actually quite related to the psychology and to this question of instinct versus search, right? Is that people make this distinction between the discrete search and the continuous behavior that is actually not there, right? Your instinctive behavior is just your compiled explicitly behavior after doing it many times. Again, there's a host of psychology literature that shows this, right? There's a few instincts that you are born with, but that's not what we're talking about. Is that the chess grandmaster's ability to look at a board and in the 10th of the section make a move that defeats you after you thinking about it for 15 minutes. What they're doing is actually not fundamentally different. From a computational point of view, they're doing the same process that it's all compiled into their neurons, which is what AlphaGo is doing, right? So it's what it's actually doing is it's compiling this, Monte Carlo tree search into the value of the neural network, right? And this is good because then so what you do is it's, here's an imperfect analogy, but we want to have you're compiling macros. What the neural network has is search macros. And that's what instinct is. A lot of instinct is these macros that you've acquired. You made all those mistakes many times, and now you have learned to instinctively not make them because that's going to lead in a bad direction. So there really is, intelligence is very confusing in that regard because it's so plastic. But a lot of this distinction between system 1 does this and system 2 does that, they're actually doing the same thing. They're just doing on different time frames.
That's right. So time is really the key element, I think, at least from what I've seen. And so what's wrong with, if I think of system 1 is any calculation that you can do in a single forward pass and some relatively small number of layers, whereas system 2 is something you can do computationally, say on a Turing machine, given more time, iteratively. Is that kind of an okay breakdown?
It's not quite. I sympathize, but here's the thing is you can parallelize, right? Take that. The Turing machine covers both of those, right? And the Turing machine is a sequential process, but I can say I'm going to start parallelizing, and that's a lot of what your brain is, that it's massively parallelism, number 1. But number 2, there's the role of learning, right? What learning is doing is think of proving a theorem, right? It's a quintessential symbolic reasoning task, right? It's the series of discrete steps, and there's a very large search space, which axiom, which inference rule do I apply now? But what a good mathematician has is that that's not how their brain works. They have all these structures compiled into their brain and all these analogies. They look at the form of something and say oh, this is like that form that I saw before. And if I tweak this, right, this is what you do, right? So the same the exact same thing that can be done sequentially can be done, in parallel.
But not without exponential blow up, right? It's like, sure, you can take an iterative circuit and you can splay it out as a forward pass, but you get an exponential blow up in terms of circuitry. And as you brought up earlier, biology is going to optimize like energetically to avoid that.
The exponential blow up is with you in one form or the other. So there's a certain envelope of time and space that you can't get out of. Now, you can, and the brain does do that, and it's important in AI, make trade-offs between spending more time and spending more space. And sometimes reducing one exponentially blows up the other. But but the real problem for us is actually those is like, we will take anything, right? Right? If we can do anything in non-exponential in any way, we will. But the problem is that you don't make a blow up go away, a fundamental blow up, if you will, if you didn't do things right, you can, but you don't make a fundamental blow up go away by shifting from space to time or from time to space. The blow up is always going to be there.
Why exactly is the AlphaGo configuration not learning? So having a discrete tree search over a policy, I mean, does that imply that Josh Tannenbaum's stuff is not learning?
Remember how Kasparov was beaten? There was no learning involved, right? And there didn't need to be. Right?
I'm not sure I follow you. There was plenty of learning that went into the construction of Deep Blue.
No, I mean, so we're talking about different.
Rather.
No. There was no machine learning.
Well, sorry. Can you? Because it seems like a dichotomy. Searching and learning. Can you explain the continuum between that dichotomy?
Yes. So, playing games is a good example, right? So, I teach students in AI class to play games with no learning, right? And most of your, PC, chess playing programs, that's what they do, right? They do zero learning, right? Meaning their state when they play the next game is the same as when they played the previous game. And what they do is they search for moves, right? This is inference, this is reasoning, right? This again is supposedly what we feel ourselves doing explicitly when we play chess is like, oh, if I move my pawn here, will you move your rook there, or will you do this with your queen, right? That's discrete search.
Okay, so you're saying some kind of model or characterization of the problem, which you can optimize against, that's learning.
It doesn't have to be model. It's like this. There's a search space, right? There's a set of all possible states of the board, right? Some states of the board are wins for me. I want to reach one of those, okay? And I have my initial states, and I have my operators, which are the moves that I could make. And now my choice is just a discrete choice of operators. This is a discrete problem by nature, right? You can't pretend it's continuous. You can embed it in continuous, blah, blah, blah. Like it's a discrete problem because you have a discrete chance of choices, which is like, which move do I make? Where do I put my piece on the board and go, et cetera, right? And now the problem, right, is that is the exponential blow up that we were just talking about. If there wasn't an exponential blow up, right, as in tic-tac-toe, it's too small, right? You could just have a table that tells you how to play, right? So in a way, the whole AI is all about where the table gets too large, right?
Yeah, but discrete problems are learnable, though.
Right.
So it's not the discreteness that's of concern here.
No, but again, there's two parts here. In every learning system, there's the learning component and there's the performance component, right? The performance component is driving the car, is playing the game, is the thing that actually does the task that you want. The performance component is what we build when we write programs, right? And in a classic AI game playing system, the performance component is doing a search over moves, right? Now, machine learning is actually, in a way, all of learning is a meta search. What it's doing is creating a performance component, right? You have a search over performance components, over what networks to have, over what sets of rules to have, over what heuristics or traditional in-game playing, and actually in a way still in AlphaGo. The main place where the machine learning comes in is in evaluating the board for how good it looks, right? And this is, the traditional AI way to solve discrete search problems is with heuristics. And the heuristic is saying like, oh, this move looks, you rate the move as to how good it looks, right? And there's this traditional ones like piece advantage, control of the center. And Arthur Samuels, when he coined the term machine learning, he was with the checkers playing program. And what he was learning was very ahead of his time, right? By self-play, just like DeepMind, was the weights, all these different factors in the evaluation function, right? So he had a whole performance system that did search, that blah, blah, blah. And there was one thing that was being learned, which was the weight of, control of the center versus piece of advantage versus something else, right? Now, of course, these days you can learn every part of this, but the learning can be continuous while the performance system is discrete. And definitely the learning and the performance system are very different. Again, this is another confusion that I think bedevils a lot of discussions of machine learning and AI, is that people conflate the machine learning algorithm with the learned model.
Right. That's
they
why
are different things. They are just completely different things. That we're guilty because, we call a classifier a system that learns a classifier, right? So we have fostered that confusion, right? Which was okay when it was, 500 of us, in an obscure field, but not anymore, right? So we got to make that distinction between the learning component and the performance component. And either of them could be discrete or continuous. And both of them in AI usually involve a search, but they searches over different things. So the Monte Carlo tree search, that is like, Monte Carlo tree search is just your quintessential classic symbolic AI inference process, search process, right? Which you could do with no learning whatsoever. But of course, what makes it powerful is that there's a neural network there's really sucking up the result of doing a lot of this search, so that you don't have to do it anymore. You can do it in one step. And this, to me, sounds a lot like what psychology shows us the human brain does.
Again, back to the discriminative models, versus generative, and kind of the conversation around GFlowNet, and where you said a lot of people maybe are going wrong in the direction is thinking that the model needs to be complex enough and accurate enough to generate real world examples, where it doesn't necessarily need to be able to do that. It just needs to be able to discriminate. But on the other hand, I think there is this notion that the brain is doing this kind of simulation. So I at least know I do that. I game out scenarios. What if this happens, that happens? So what's producing those samples or those possible world models? And if you could just talk more about this distinction and what you think of say GFlowNets or similar.
Yeah, this is absolutely, exactly. This is a crucial question in my view. And here's the thing, is that if you can have a generative model of the world that's accurate, you're in great shape, right? But the problem is that, and the problem with a capital P, is that a full generative model of the world is just impossibly costly. In memory, in energy, in inference time, it's just infeasible. So you can, stamp your foot and say, like, you got to be principled, but you'll die while everything else survives. We got to, and the idea of discriminative learning, and I mean, I totally understand where this comes from. And I used to kind of like sympathize with this back when I was a grad student, and then I learned better, right? Is that in a way, and a lot of people, even out in science, right? Machine learning is now, penetrating every science. And there's like often this like, reaction of dislike, because, machine learning is like this. Oh, you gather a bunch of features and then you do great descent on them, and you hack and you hack and you hack. And then I do better than the scientists. And the scientists get really frustrated with this, because it's like, you're just hacking. You don't have any fundamental understanding of the process that generates this data, the phenomenon, the generative model, right? And then they think that this is all that machine learning is. And then when I talk about, no, there's this part of machine learning that deals with generative models and blah, blah, blah. And then they start to smile and they start to get closer to nirvana, right? So I understand, right, that the scientific impulse to model things properly as opposed to just hack a bunch of stuff, right? But here's the thing. We are a part of evolution, and our artifacts are we also doing evolution, right? And in evolution, the supreme rule of the universe is whatever works. And, a fly has a discriminative model of the world because that's all it needs. Putting a generative model of the world on a fly would be stupid. That fly would die and the others would live. Now, right? So, and the same thing in AI, right? Like, we had 50 years of low progress in AI until people in machine learning said, what we're going to do is set all this aside and start learning on real data from day one. And we're going to measure accuracy on real data, right? And that led to a lot of hacking, but that also led to where we are today. Now we come to your question. So this is why, in some sense, discriminative learning is actually better founded, more fundamental than generative learning, right? But now we come to very important questions like, what about the simulation that I'm doing and you're doing, and we all know we do, and it's so powerful, and predictive coding requires, right? So I think that what happens is that as your brain gets more powerful and you have a more powerful sensorium, because your ecological niche, calls for it, say humans, like once you have more powerful vision and a wider range of behaviors that blah, 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 then I've also observed this happening in my own research in AI, which kind of, is interesting, right? And a lot of people are like, then your discriminative models start to get more and more powerful, more and more flexible, and you start to discover more and more general things. So a generative model is what a discriminative model evolves into once it gets sufficiently powerful and flexible, right? You want to start to detect these invariants, another very important idea. And as you detect more and more invariants, you start to have something that's more and more like generative model. No, but now at the end of the day, what you have in your brain and what you have in predictive coding, we have this illusion that it's a complete generative model of the world, but it isn't, right? Full of tasks and things where you just learn and apply the things that you need to in order to guide your action. Predictive coding does not exist for its own sake. It exists to guide your action. So any part of your sensorial of the world model that's not needed to guide your action goes out because it's wasting energy and making you less fit.
I appreciate that you said that generative models are very costly, but there are many folks in the space, I mean, like Max Welling, for example, that really say we need to have generative models. But the thing is, we know, I don't know whether you saw our latest episode with LeCun, but Randall Balistriero had this spline theory of neural networks, which basically says that neural networks don't extrapolate in the sense of continuing the pattern. They kind of are interpolators. So presumably these generative models are very convergent. They don't really extrapolate outside of the training distribution. But just to finish this point, so what we really need to have, if we are using our imagination, is genuine extrapolation. And I think what Benjo is doing with this GFlowNets is, rather than picking the most likely reward trajectory, he's kind of deliberately disadvantaging it on average by, kind of allowing it to sample lower likelihood but higher entropy, trajectories that would give you more information gain. But there's something really fundamental there, isn't there, about being able to explore the unknown, not just the things that we know about.
I mean, absolutely. So there's a couple of points here. One is that I'm not arguing against generative models, if you notice, right? I'm arguing against properly understanding how they emerge and what their role is. We shouldn't be prematurely trying to learn generative models in situations where they don't make sense. At the end of the day, your brain does have a very powerful generative model of the world, right? It is able to generate, dreams and like it's able to generate, the features that it then, compares with the world by predictive coding. So again, I'm not arguing against generative modeling. I'm arguing against understanding it properly and doing it properly. Now, what does that mean, right? And this is where so what a lot of people, I think, including Joshua, are trying to do is actually what predictive coding does better. Right? Actually, this goes back to predictive coding, which is like predictive coding. Again, to paint the cartoon is like this. Your sensory data is coming into your thalamus, right? From your retina via the optic nerve and whatnot. And what predictive coding is doing is comparing not just one candidate model, but a whole bunch of them. In fact, my view is that it's actually very cleverly and efficiently comparing an exponential number of models. We could go into the details of that, but it's effectively in non-exponential time, in linear time. This is where ideas from some neural networks and so on come in. It's comparing a whole bunch of models at the same time and seeing which one wins. And, this is a constant in the work of the deep learning people, particularly the work that tries to be more powerful, and the energy-based models and the contrasted divergence. And this is always because in order to generalize properly, I also need to know what it is that does not hold. And then they go into all these things that are so painful, Monte Carlo this, and we'll get another, decades of that, right? And it's you don't need to do that. What you need is if you have this process of comparing, even doesn't have to be exponential, but exponential is actually very useful. Comparing your 100 best models, not random, not small artificial, digressions from the truth, again, Max Welling also has, and all this work is interesting, but I think it's kind of doing something in a more difficult way than is necessary. There's this very salient fact about the brain, right? That all our models are feed forward, but in fact, the feedback connections outnumber them by an order of magnitude. I don't know if you know this. There's 10 times more connections going back than forward, right? It's not just that we're not capturing what's going on. We're not capturing 10% of what's going on. And one theory of this, which I don't know if it's true, but really resonates with me, is What are those feedback connections? They're precisely all those models, right? Your brain has all these models, and feed forward this one reality, and the errors in that reality, like, because this is a very, clever multi-level process, like you're only propagating the errors, right? If your simplest model, quickest model of the world explains the data perfectly, it stops there, right? And you have, a reaction that doesn't even go to your cortex, right? So we have one reality going forward. You have an exponential number of models going back, right? And those are the high value targets. It's like your second best model, your third best, your fourth best, right? If your second best model turns out to be the best one, then its weight goes up, as it should. So this is actually, this whole thing that like Jan really likes to like have, you have the energy landscape and you pull down the energy of the good parts and up the energy of the bad parts, right? And that's how you learn, right? The way to do that is to always be comparing your best models, right? And again, this can be done even better than that I'm letting on because of this exponential aspect of this. And then the energy, of the bad parts goes up, right? Because they fail to match the incoming data. This, I think, is the right to do things, both in terms of efficiency and in terms of generalizing better. So it's a win-win, and I don't know why everybody's doing it this way.
So you must then have some sympathy for Jeff Hawkins' kind of thousand brains, where it's like, hey, these cortical columns are all doing kind of their own independent little model generation, and then there's a voting, kind of scheme where out of these thousands of possible worlds, they kind of converge on which ones they think are most likely.
I used exactly the right words. I have some sympathy for Jeff Hawkins. Some sympathy
for his ideas, I meant to say.
Yeah, exactly. I think so. Like I read on intelligence. I haven't read, the more recent book because I lived through it, and it didn't rise enough in my priority list, maybe mistakenly so. But I read on intelligence when it came out, and I both liked it in some ways and didn't like it in others. And I've heard him talk and since and whatnot. And I think, I understand what his frame of mind is. And what I like about what he's doing is that, interestingly, because, his background is not in neuroscience, he's actually, his criticism of the deep learning folks is very valid, is that like, you guys say you're inspired by the brain, but that's BS.
Right, like the point you just raised, we're doing feed forward, and we've missed the 9x feedback.
Yeah, and again, if you listen to what Jan says, right, I think it captures it well, which is we should be inspired by nature, but not too much. Which, from an engineering point of view, is fine. But the thing about engineering in AI is that it'll only get us to local optimum. To get to the global optimum, I think what Jeff is doing is very honorable, and I wish him great success. He actually spent a lot of time talking to the neuroscientists, understanding the latest neuroscience, and trying to port that over into AI. Like, more power to him. There should be thousands of people doing that. There's more. He's not the only one, but we need more of it. Having said that, at the end of the day, unfortunately, what he managed to capture about what's going on was very small. And there are several things in his approach that I think are actually off base. Having said that, trying to understand here I think what I think are some key ideas that people have neglected. The unit of computation is not the neuron, it's the cortical column. Very good. You can't think in terms of the cortex. You have to think in terms of circuits that loop through the cortex and the thalamus and the hippocampus. You will not figure this out if you don't do at least both of these things, right? And there's a few more like that. And so like I'm 100% on board with that. Now, unfortunately, this is no big strike against him because the problem is hard. At the end of the day, he hasn't been able to take these ideas very far. And ironically, when it comes down to actually doing things, what he's doing winds up not look too different from what people have been doing in machine learning for a long time, which he also kind of often unfairly, cartoonifies and says like, oh, this is all that you do. And there's a lot of other people doing this. So I agree with that thrust. I wish, he'd made more progress.
Yeah.
But I think eventually, escaping deep learning right now, it is in a local optimum, and I think that is a path to at least a deeper local optimum.
That's right. I mean, just quickly, there are a couple of things I love about Jeff Hawkins. I mean, first of all, this idea of strong multimodality. So all of these cortical columns are informed by different sensory motor circuits, and that's wonderful for robustness when you're getting signals from different sensory motor circuits. And also, he overcomes the binding problem because they are, these, as Keith was saying, they're voting and they're talking in complete objects, not in parts of objects, which is really interesting. But the thing is, though, because you keep talking, I mean, Hawkins is an emergentist. He thinks we should go down to the really low level and all of this magic stuff will happen. On the other side of the spectrum, the symbolists think that we should model the brain, or Marvin Minsky's conception, we should have a vision model. People like Jan LeCun are kind of saying, okay, well, we're nearly there. We need to incorporate causal, like if we had the action chain and the models could do causal reasoning, then that would robustify things. And there's everything in between. The linguists are saying, well, you can't have the semantics of similarity. You need to have, grounding, and you need to have first order logic and so on. So there's a whole spectrum, isn't there?
There is. And I mean, you've probably had this experience. Like when you talk to the symbolists, they're very, very hardcore about their position that like trying to look at things at the levels is ridiculous. When you talk to the emergentists, you also, the bottom up folks versus the top down is another way to look at this, right? You also have people who are like very strongly convinced that this is the way to go because there's all these things wrong with doing things at the symbolic level. And what I think is that they're all correct and they are all wrong. The thing is that AI is a very hard problem. And this is a lot like, the blind man and the elephant, right? It's like, to start with a symbolist approach, right? There's this famous thing called the physical symbol hypothesis that Newell and Simon enunciated, which is basically saying, or like Mars levels, right? It's probably more familiar to people these days, is we should do our research at that level of abstraction, ignoring the implementation. And honestly, there is a lot of merit to that, because you will lose the forest for the trees if you don't keep that perspective in mind, right? And it is mathematically true that, any symbol system, it's Turing machines, right? Having said that, and I think this is kind of what's a little more subtle, and unfortunately the symbolists kind of didn't cotton on to, is that thinking about, so that it's not that the hypothesis is incorrect, it's correct. And it's not that it's not useful, it is useful because it allows you to abstract a lot of details, but it leads you in the wrong direction. It leads you in the wrong direction because, for example, we're just talking about energy. And if you really look at how the brain works, the energy constraint is such a powerful force acting on everything. But if you do things at the physical symbol system, you don't even talk about energy. So you just missed out on a lot of real useful constraints for figuring out intelligence. Why would you want to do that? Why would you want to shoot yourself in the foot like that, right? So that I think is one aspect. Now, when you go bottom up, right? I think, and again, in contravention to the physical symbol system hypothesis, so part of what makes this problem hard and makes people talk past each other is that it's not just that there's like the neural level and then there's like the, symbolic level. There's 100 levels here that we haven't figured out yet, right? For example, going from individual neurons to cortical columns to the circuits that, involve the thought, right? We already know what some of these levels are, right? So the problem is that like, there's all these levels that we haven't been talking about. And instead of like trying to do this dichotomy between A and B at the ends of the spectrum, we got to start populating this, right? But having said all that, and again, this is an intuition, I can't prove it to you. It's like what we have, computers are very different from brains in many regards, right? In computers, we cannot do and force by design, because it's convenient for us, a very strong separation between the architecture and the operating system and the applications and whatnot, because otherwise we wouldn't be able to deal with it. But the brain isn't like that. In the brain, you still see a lot of the flavor of the lowest levels at the highest ones, which probably has a lot to do with the fact that the brain evolved and emerged and wasn't programmed by someone, right? So, and again, the physical symbol hypothesis causes you to ignore that, which again is a big loss, right? I think a lot of how we behave, even at the conscious system 2 level, is directly related to the substrate, like the lowest levels. So I actually do think, counter to a lot of the symbolists, that the lowest levels do have a lot to teach us about the highest levels. But, right, when I have to choose what research to do, right, I'm not super excited about going bottom up because it's such a long distance to the goal. You're just going to spend your entire life on stuff that's going to get you epsilon closer, right? I think you need to like try to see, again, I agree with Mar in that regard. You need to, understand things at the computational level to just have a handle on them, right? Otherwise, they're going to spin your wheels forever.
Apparently, Lisa Feldman Barrett said that this, Paul MacLean's notion of the triune brain and this idea that there are old parts of the brain and new parts of the brain. She said that was one of the biggest myths in all of science, because of course they've co-evolved together. But we were just talking about, LeCun's assertion about. I mean, everyone says causal representation learning is going to be brilliant. Actually, Benjo talks about it as well. There are loads of folks actually trying to learn the causal structure from observational data. What's your take just on that whole thing?
I think causality is a very problematic word, right? Every time I hear the word causal, particularly coming from deep learning, it's one thing to hear the word causal coming from to the Perl, right? I know what that means exactly and what the ins and outs are, maybe the pros and the cons, but that is a very, well worked out notion of causality. When I hear the word causal coming from deep learning people, I start to get nervous because I think a lot of what people are calling causal is, it's another one of those words, right? I think you could say, this is not quite what I think, but it's a good reference point that causality is another one of those useful illusions. Space and time are useful illusions. Free will is a useful illusion. Causality is another one of those useful illusions, right? What is causality really, right? And then it's also, it's another one of those like context. Oh, we're missing context. It's like one of those magic words of like everything that your learning system can't do, right? You just, sprinkle this causal pixie dust on it, and then suddenly everything is brilliant, right? It ain't gonna work out, right? It's not gonna work like that, right? So what do we? So let's start. Maybe the best way to do this, like start from like we have these learning engines that are great at discovering correlations, right? They could be even better, but let's just take that as a given. Like we're very good at discovering correlations right now. What is missing? Right? First of all, is something missing? I do think that something is missing, right? But what is it that's missing, right? What's missing is that the goal of learning is not just to predict accurately. This is how you evaluate a learning algorithms, is predictive accuracy. Like this is amazing. This is a methodology that's gotten us very far. But you have to realize that prediction is not the end goal. Prediction is subservient to action. The whole point of learning and predicting and the generative model and all of that is to guide your action, right? And in order to guide my act, and this in your brain and in any AI system, any reinforcement learning system, at the end of the day, the point is you want to take the best actions that will maximize your reward, your fitness, whatever, right? And predictions are not enough to take actions. I have predictions obtained by observing the world, right? You have to be able to predict the results of your own actions. This is what causality is, right? Causality is being able to predict the effects of your actions, even if you haven't taken them before. That's the key. If I've taken actions before and gathered data, I can learn their effects by purely correlational learning, and then I don't need causal anything. But of course, most of the time in both nature and society and technology, it's like, you got to consider a space of actions, and the larger the space, the worse the problem gets, right? You have more power, but you also have a bigger problem. It's like you have to be able to predict the effects of actions and sequences of actions in particular, like sequences of moves in the game that you've never taken before, right? And now this is a very different ball of wax. You can't just do that by correlation, right? Another question is like, how do you learn that, right? And the way I look at, things like all of these theories of causality, right? Maybe it's a very machine learning way to look at it, is that like, these are inductive biases. A theory of causality is an inductive bias that lets you generalize from the results of actions that you have taken to the results of actions that you have not taken, right? This is all that causality boils down to. And by the way, there are formal theories that work like this. Like, like Phil David, for example, when a well-known Bayesian statistician, right, who's quarreled, with who they in the past, right? He says, we don't need any of this. All like statisticians are very resistant to causality, partly for historical reasons, partly for bad reasons, which who will tell you about. But I think partly, at least from the Bayesian statistician's point of view, I understand their resistance because it's like this: if I have decision theory, right, my decisions are part of my space, right? And now what I'm doing is like I'm conditioning on my actions, right? I condition on the world's behavior. I learn my action. I predict the result, right? This is what reinforcement learners do. And if you can do that well, you don't need to talk about causal. I think you do need to talk, or it's advantageous, convenient, again, it's useful to talk about causal because you do want to focus on this problem of predicting the effects of actions that you haven't taken. But this is really all that causality is. It's not some magic thing that that solves all problems. And I think,
Right.
So it's important to do causal learning in this sense, but I also think it's also important to not lose our way doing all sorts of things that aren't going to solve the problem because, this is the problem that you have to solve.
I oftentimes think about causality in the context of this inherent asymmetry between both the past and the future and knowledge and control. And I love this quote from Shannon, which I heard many years ago, and it's really what set me off on this line of thinking, which is he said, we have knowledge of the past, but cannot control it. We can control the future, but we have no knowledge of it.
Yeah, in fact, I sympathize with that thought so much that, there's this debate about what is time, right? Like physicists, for example, are very much into this. And usually they wind up saying, well, it's entropy increasing and whatnot, which I find very unsatisfying. I actually think it's actually closer to the truth of why do we have this notion of time, right? It's like, this is the real distinction between the past and the future is between control and prediction, right? It's like, if you take everything, right, and separate it into the stuff that we know very well but can't control and the stuff that we can't control, right? If you think about convergent and divergent processes, when there's a divergent process is when we have the opportunity of control, and that's when those things are in the future, right? So I actually think there's, we're not there yet, but I think there's a lot of promise in thinking about things that way.
We were looking at your Twitter earlier. You said, if information is conserved and the universe is finite, it's also cyclical, and the entropy law is false.
Before you respond to explain that, though, I'm curious. Those tweets, you're just kind of sitting around and you go, you know what? I'm gonna throw out a tweet about entropy and its implications on the universe, or did it come from what was the context that generated that tweet? I'm curious.
No, I'm glad you asked that question because I think some people have the wrong model of what I tweet and why. I don't throw stuff out that just occurred to me. Number one. I don't throw stuff out just to be provocative or to say whatever, right? The things that I tweet are either things that I believe in, could be wrong, or hypotheses that I think are plausible and deserve consideration. And usually behind every one of these tweets, there's actually a lot of thought. And we could do a couple of examples. So and usually and then some people, if people follow up, then I will often elaborate a little bit, right? But any one of these tweets, I could write a whole article about it, except, there's no time.
So what's the category on this one? I'm really curious what the greater purpose was.
Well, so I didn't say that there was a greater purpose, there is a greater purpose, but I think when you're doing research, right, you think about things, and you follow your instinct about this is interesting because it might have important consequences. You might not know exactly what they are, right? There's some things that you do with a very concrete action purpose at the time, but thinking about, the nature of space-time is not one of those. Although eventually that might even have bigger consequences than anything else. But what is behind a tweet like this one about entropy, right? I think that physicists have confused themselves about the entropy law for, almost 200 years now, right? And we are all confused along with them, right? And this confusion is actually holding us back, right? And what is the confusion, right? We could go into more details about what, the things that people have written about this, going back to Boltzmann and Gibbs and whatnot, right? But let me give you a modern AI take on this, which is what's behind that tweet, right? And I had other tweets related to this saying some of these things, but let me tell you the second law without mentioning the word entropy, which I think is incredibly enlightening, right? Okay. The universe is a Markov chain with a very, very large state space, evolves step by step. And very importantly, it's a symmetric Markov chain. It's a symmetric Markov chain, meaning like the probability of transitioning from A to B is equal to the probability of transitioning from B to A for any two states A and B, right? I mean, this is the basic fact, right? Like of Newtonian mechanics and, and quantum, Hamiltonian unitary evolution, et cetera, is that things are reversible, right? Like my probability of going from one, I'm just as likely to go from this state to that state as vice versa, right? This is the confusion with entropy is that but then macroscopically, this is not what you observe, right? But this is like, if we believe in the laws of physics as we understand them right now, which we could, go into, but let's not right now, right? Then these probabilities are symmetric, right? So the universe is a Markov. So to summarize, the universe is a symmetric Markov chain, right? Therefore, it is like a basic piece of math, right? That's like, completely trivial, stats 101. It converges to the uniform distribution, period. I mean, not period. There's various conditions of irreducibility and blah, blah, blah. But again, setting those technicalities, there's some stuff there, but ignoring that, which is not relevant to this discussion. If you are a symmetric Markov chain, you converge to the uniform distribution. Because in detailed balance, right, the probability of being in a state A times the probability of transitioning it from A to B has to be the same as the reverse, right? If the transition probabilities are the same, then detailed balance can only be satisfied if the probabilities are the same as well. It is just mathematical, right? It's like, there's nothing complicated about it. But what this means, think about it. So if the universe is a symmetric Markov chain, and we have very good reason to believe it is, right? Then it's going to converge to the uniform distribution, right?
Okay.
This is a cosmic statement. And entropy is just a measure of how close you are to the uniform distribution, nothing else, right? Entropy is increasing. It's not that entropy is increasing. Sure, you can frame things that way, but they framed it that way because they didn't know about Markov chains back then. They were invented by Andrei Markov in 1913, long after all of this. If people had been studying this back when they were, and then there was this thing of like continuity, like people think in continuous terms, but you can do all this with continuous time as well. But let's not do that, right? So
I was going to ask that. Does it change anything having a discrete Markov chain to represent states in the universe?
I mean, of course it doesn't, because the universe is not continuous, right? Continuity is just a convenient approximation to a discrete reality. Again, people are so confused about this, right? Like, again, I've talked with many people about this, physicists and non-physicists, and people have, I
think to be fair, it's an open question. It's not known whether it's continuous or some underlying, lattice or discrete thing, right?
I mean, fair enough. And by the way, this gets back to, so before we continue this, just to close the previous point, right? If the universe is discrete, right, then there's only a finite number of states that it can cycle through, right?
Well, and
at some point it's going to repeat.
So to answer your question directly, if it is continuous and you're dealing with continuous variables, what happens is you generalize to, you'll get arbitrarily close to any particular state, given enough time. So there's like this little C or whatever. So you'll cycle back like arbitrarily close to any state.
Right, but that's precisely what never happens. And now you say that whether the universe is continuous or discrete is an open question. Well, in science, all questions are always open, right? But let us...
What I meant by that is there are people on both sides of that equation that are adamant.
Absolutely. And I'm adamant that the universe is discrete, and let me tell you why, right? I did not come to this conclusion casually, right? And I could be wrong, right? Like I could change my mind tomorrow, right now, if you prove me wrong, right? So like, but here's, I think, what is the way to think about this like good scientists. Let us set aside all of that continuous math that, we've had since Newton, and that quantum mechanics is also full and whatnot. Like, math is models. Models are convenient. And by the way, I'm not against continuity, infinitesimal infinity. Again, they're incredibly convenient. Like, I use them all the time. So I'm not against that. But if you want to get the fundamentals, right, you got to look at observations, right? No one has ever or will ever make an observation of something infinitesimal or infinite. Observing something infinite is impossible, right? So let's set that one aside for a second. Infinitesimal is a more interesting question, right? Like, has anyone ever measured an infinitesimal small quantity? No, of course not, because, things are quantized, right? Has anybody, and that people accept, right? It's like, there's the two-slit experiment and things like that. And, and you see those pings one at a time, right? And then, I've actually done this. Like, you have to go through and look at like all these observations that people make in particle detectors with Geiger counters, with like this, that, and the other, right? Like, like with photo detectors. Your eye, your retina, rhodopsin is this protein that detects light. What do? They all do the same thing. They undergo a discrete state change. There is no continuity there. What does an atomic clock do, right? And then people accept this for, quantities like that. They're like, oh, but space and time, you don't know if they're continuous or discrete. It's like, have you measured the continuous infinitesimal piece of space or time, right? Let's think of time for just a second. Like an atomic clock, right, is an atom flipping discretely back and forth between two states, discretely.
So let me agree
and
with you.
And you cannot measure a period of time that is short. There's like nothing happening between those. So at the most basic level, space, time, and all quantities are discrete. Like, so how can anybody believe otherwise?
Well, let me agree with you on that point. Let's posit that every observation ever made, is of finite precision. It's discrete, these quantum events that occur. But here's the kind of remarkable thing, at least the remarkable thing to a lot of folks, including myself, is that get that part, however, those observations are described so well by these smooth, continuous models. And so then you get to this kind of deeper philosophical question, are they ontic? Are they real? Is there something actually real continuous? And I'd really like your take on that, which is, how do we know that we're not just sitting on top of this ontic, this real underlying smooth thing, but all we're ever observing are discrete, aspects of it?
Yes, I mean, so, and indeed, I think the more informed people, that is the argument that they will make, right? They will accept that all our measurements are discrete, right? But now here's the thing, like, what you're saying is an illusion. It's like the illusion that people have that there were no fractals.
The challenge I would have there is the way in which it's not illusory is we don't actually have any discretely defined mathematics that can reproduce the predictions of these continuous mathematics.
No, very good, right? So you just hit on the crucial point, right? Now, but before we go to that, let me mention another thing, which is renormalization, right? So the beauty of continuous math, right? That goes back to Newton, and this is amazing, right? This is like one of the most amazing things ever. Is like he posited these laws based on extremely low precision data, and then they were valid to 10 more orders of magnitude. This is mind-boggling, right? And that's why we believe in continuous anything, right? This is extraordinary. Who could have predicted that, right? It boggles the mind, right? But it has reached its limits. Quantum field theory is bedeviled by these infinities that you get by trying to sum over continuous, by trying to integrate over continuous things. Like, why do the path integrals keep diverging? Why do they need all these hacks? It's like something is going deeply, deeply wrong there, right? We've reached the limits. So why wouldn't we, right? I mean, come on, right? Do you really think that would go on for we probably know that at the Planck scale, right? Measuring something more finely requires so much energy that it creates a black hole, so the information doesn't get out. So
yeah, sure.
One way or another, that is dead. But to answer the really important point, right? I mean, Feynman famously said, right? And Feynman was the guy who created all of this path integral stuff and whatnot, right? And he said, like, I get all these letters by people saying, like, oh, but like, is space really continuous? And, all those complicated amplitudes, do you need them? And his answer, which is completely right, is like, give me a better option. It's not that he believes deeply that space is continuous. It's that, the other options that we have do not work as well. And that is the reason, right? But I think I'm all for that, right? We should use those things because it's what we have. But we shouldn't start to confuse them for fundamentals. And moreover, I mean, it's interesting because in the history of quantum mechanics, once people discovered this, there was a period where there were these statements by I think Schrodinger saying like, continuity is just like this horrendous, monstrous notion. Like, who could possibly believe such a thing, right? And I agree, but then they got stuck, right? And we have to respect the fact that they got stuck, right? They really bumped into real difficulties. So you are right that continuous math, in a way, is an amazingly powerful tool. But we shouldn't give up on doing better. And I'm not giving up on doing better. And, I'm
curious
on how you might do better.
Yeah. I was about to ask that, which is, do you have a favorite discretized, or let's say a favorite direction that people are trying to pursue for discretized, theories of everything? Is there one that stands out to you as the most promising?
No, I mean, of course. So if you look at the state of physics today, right, there's the string theorists who, in my view, are like, going completely in the wrong direction, sorry. And then there's the loop quantum gravity folks who have the right idea, right?
Okay.
And they, even the string theorists these days, after, 20 years of hard knocks or 30, pretty much everybody at this point believes that, yeah, space-time is going to be discrete in some way. The question is how, right? And if you come at this from like a computer scientist's point of view, like string theory is physics for electrical engineers and loop quantum gravity is physics for computer scientists. It's like space is a graph. There's relations. There's nodes. And I'm like, what's not to like about that, right?
So is this kind of like the hypergraph models of Wolfram or
no? That's his own version, right? Wolfram is one guy, right? We could talk about what he's been doing, which is interesting and also has its problems. But loop quantum gravity, like, so there's this whole approach to that goes back to to John Wheeler, and like it's many decades old, but like it's trying to quantize gravity, right? And when you quantize gravity, inherently you quantize space-time because space-time is gravity, right? That's what general relativity tells us, right? So they have been trying to quantize space-time, for decades. And I agree with the general thing that they have very complicated schemes to do this, overcomplicated, unfortunately. But again, and then they wind up being like this continuous elements. And so even though I sympathize with that direction in general, they've also gotten stuck. And I don't think they have the answer. Now, I think there's an answer to be had that no one has had yet. And it may be coming, this may happen tomorrow and it'll be one of the greatest, revolutions. It'll be like quantum mechanics in the 20th century. So it's coming.
Well, I'll tell you a funny comment I heard by Roger Penrose, which was somebody was asking him about loop quantum gravity. And he said, I think they've kind of gotten it backwards. Instead of trying to quantize gravity, we should be trying to figure out how to gravitize quantum mechanics. So I don't know, I'm not sure which side of that coin I come down, but it's an interesting thought.
That's a very Roger Penrose thing to say, because of course he's you always understand people by in machine learning or physics or anything, like what is deep down in them, what is the theory that really resonates with them. And for him, it's general relativity. He's a minority among physicists. To him, nothing exceeds the beauty and the power of general relativity. And quantum mechanics is like this ugly pile of hacks, which it is, but it works and it's more important. But my answer to that is that neither. I don't think you need to reduce gravity to quantum mechanics or quantum mechanics to gravity. That both are those, paths into a wall. What you need to do is to reduce both to something deeper. And in fact, I think it all goes back to Newton. It's all Newton's fault, right? He gave us a lot, but he also got us into the things that, like, relativity is a departure from Newtonian physics in one way. Quantum mechanics is a departure from Newtonian physics in another, right? But the problem is that there are a lot of things about Newtonian physics that are still wrong in Newtonian physics and have been inherited by gravity and quantum mechanics, in particular what space-time is. And this is where I think we need to solve the problems. Like, we actually need to go back to Newton and overturn some of what he did to be able to reconcile, quantum and for example, right, what is time, right? There's this guy, Julian Barber, that has a theory of time that to me is really perceptive. And what he did was like really go, and again, if you look at these things from machine learning point of view, it's quite fascinating. It's like, I'm going to put this in a way that he never would, but it's like time is a latent variable that we have induced to relate the things that we do observe. Exactly. And so is space. And so are fields and so are light. These are all latent variables. And what we need is a better set of latent variables. What we need is a better set of basis functions, right? There's this something like, oh, is it particles? Is it waves? No, those are both bad basis functions. We need a different, better set of basis functions. So I think we need to reduce space and time to something deeper, and that's when all of this will come together.
Fantastic. Well, Professor Pedro Domingos, it's been an absolute honor to have you on the show. Thank you so much for joining us.
Thanks for having me.